So, we are going to finish today the monotectic and syntactic phase diagrams, and I have already discussed the phase diagram of monotectic systems and their solidification behavior of different alloys. So, I am going to today talk about the free energy versus composition diagrams of these typical monotectic phase diagram, and subsequently I will discuss about the syntactic phase diagrams. So, let me just go to the board and show you how these free energy versus composition diagrams will look like. So, first I will draw the same monotectic phase diagram which I have drawn in the last class. This is for any system A and B as a function of composition, temperature. So, this is the melting temperature of pure A, melting temperature of pure B liquid, and this is the Tc above which single liquid present and below which it separates into two liquids alpha, alpha plus L1, alpha plus L2 and alpha plus beta, and this is beta. Okay, now there is some problem here, let me complete it. So, this phase field is beta. So, now we are basically going to draw, I am going to basically draw the free energy versus composition diagrams or G versus XP diagrams at different temperatures. So, let me just draw the temperatures. So, this is at T1, so then this is at T2, this is Tm, T3, Tb and at temperature T4. So, there are 5 temperatures T4, T, this is eutectic temperature at T, T3, Tm, T2, T1, correct. So, as I told you that when you draw the free energy versus composition diagrams, we need to consider all the phases. So, what are the number of phases present here? Alpha, beta, L1 and L2 and liquid. So, you could understand 1, 2, 3, 4, 5 phases, but basically L1 and L2 is a decomposition products of the same liquid L. So, we will draw one plot or one curve for both L1 and L2 and we will show how it is possible. As you have probably seen in all my last plots, this is G which is versus XB and this is at T equal to T1. So, what happens at T equal to T1? At T equal to T1, you see from the A rich end to the B rich end, L1 is stable for a particular composition range, then alpha L1 plus L2 and then liquid L2. So, let us use the different color chalks today. So, I will use red for liquid, okay, and green for the beta and yellow for the alpha. So, alpha will be above, okay, this is G alpha or rather, and then this is beta, beta will be even farther above because beta is stable, not stable at all at this temperature, and for the liquid this will be like this, this is Gl. Okay. So, as you clearly see, this is the relative disposition of these free energy curves. Now, liquid curves looks like a typical, it is a typical hump, it is just like a hump or bump on a road. So, this indicates that the liquid is, so I draw a common tangent. So, this is L1, this is L1 plus L2 and this is L2. Okay. So, this is at temperature T1 in which only two liquid phases L1 and L2 are stable. Now, let us draw it at temperatures at T2. At temperature T2, you see here this is temperature T2, alpha is stable for a small composition range in the air each end, then alpha plus liquid, and then L1, L1 plus L2 and L2. Looks like very complex, but it is not. What will happen is that alpha curve will come down and have a crossover with the liquid curve. That is what is going to happen, because as you know, when there is a two phase field, one solid plus one liquid, you are going to have crossover of solid and the liquid free energy curves. So, let us do that. So, yellow for the alpha. So, alpha curve will come down and then go up, okay, and beta anyway will be much above. So, let us not even talk about it. Let me just increase this little further, so that it looks better. This is G beta, G alpha, and liquid curve will have a crossover, but it will remain similar shape, retain the shape like that hump. Okay, so, now what I will do, I am going to draw a common tangent between, this is for the liquid, common tangent between this and this, sorry. Okay. So, that tells me this is alpha, this part alpha free energy curve is the lowest position, this is for alpha plus L1, and I again have to draw this kind of common tangent here between in this what is called in the for the liquid, and then I got this. So, this tells me this is L1 plus L2, L2, L1. So, you got it right, alpha, alpha plus liquid L1, L1, L1 plus L2 and L2, but very easily obtainable. Why? Only change between from these to these is that here the alpha free energy curve has come down on the air each end, you can see here air each end, and have a crossover with the liquid curve. Okay. I hope that part is clear. Now, let us do 3 curves, I will need to draw it here, otherwise you will not be able to appreciate. All 3 of them I will draw here. So, this is at temperature T equal to Tm, temperature T equal to T3 and temperature T equal to Te, correct. So, if possible I will draw at T4 also. So, at Tm what happens? At Tm actually you have the monotectic reaction, this is a Tm, you have a monotectic reaction taking place, and monotectic reaction is given by L1 going to L2 plus alpha. This is the monotectic reaction. I have discussed a lot about this in the last class. So, this is the monotectic reaction. At Tm this is what is going to happening. So, what will happen? All the 3 phases will coexist, alpha, L2 and L1, the phases will coexist. Let us draw that. Beta will not at all be present. So, beta curve will remain above. Now, alpha is this. So, alpha, this is G alpha, and this is okay, liquid. So, what I do? I draw a common tangent between all the 3, then I get into it. So, you can see this is alpha, then this is alpha plus L1, L1 plus L2 and L2. That is what I see, alpha, alpha plus L1, L1 plus L2 and L3. Sometime you will see that some of the books they will write the whole region, this is a common tangent between G alpha and GL, you will find they will write alpha plus L1 plus L2, that is also correct. So, now it is clear that how the disposition of the alpha curve is taking place. Alpha curve is slowly coming down. Now at T3 also is very simple. T3 is basically there is no L1, so liquid curve will change. So let us do that. At this is at Tm, this is at T3, this is at T1, this is at T2. Okay. So what will happen at T3? Again beta will be above. I don't need to think about it how it will happen. I need to draw it. You cannot skip the beta curves on the diagram. So now alpha obviously is present here at T3. So alpha will be coming like this. This is G alpha. Okay, and liquid curve will change the shape. What the shape change will happen? Okay, this will not be this kind of shapes. This will have only this crossover, and little bit lower slope. Okay. So as you see, there is a crossover between the liquid and a alpha curve, and this requires you to draw a common tangent between them, and this is alpha plus liquid L2, and this is L2, because at this temperature L1 is not at all stable at T3. In fact, below Tm L1 is not stable. So that is why it is single liquid L2 which is stable, and that is why this free energy curve of the liquid will be having same shape like alpha and beta. It will not have a hump anymore. That means it does not have any miscibility present. All the miscibility what was present, miscibility is present, all the miscibility what was there are dealt with at a temperature above Tm. So what will happen at Te? Very simple. Te is same what I have drawn. There is alpha plus beta, both the phases are present at Te, and liquid obviously. So here a beta curve will go down. So first is alpha is in yellow, and beta will be also like that, but before that we should draw the liquid, yes, liquid. Okay, this is Gl, and subsequently I draw beta is present at the right hand side, yes, this will be little bit down, otherwise common tangent cannot be drawn. Okay. So these things you should practice, then only you will get. There is a common tangent between G alpha, G beta and Gl. This is G beta, the green color text, and so you draw a common tangent here. So this is alpha plus L2 plus beta and beta. That is what you see here in the T. So at lower temperature the liquid curve will go above and both alpha and beta will be crossing over. There is nothing else will happen. So that is it. So let me also draw it, because some of you may be having problems at T equal to T4. So liquid curve will be much above. This is Gl. Alpha and beta will make a crossover. And you draw a common tangent. Oh, sorry, color needs to be changed, right? This is alpha, this is B alpha, and this one is beta, and then I draw a common tangent between them. So this is alpha plus beta and beta. So from this onwards, this is same as your eutectic phase diagram. Okay, I hope it is clear. So if you look at a snapshot, of these pictures together, then you will be understanding. Remember, I will again write, this color is for liquid and this color is for alpha, and this color is for beta. This is the color code. So, if you know that, then you can easily understand this. That is all for the monotectic reactions. So, now we will discuss about syntactic reactions, and I quickly go back to the syntactic thing. Syntactic reactions are also phase diagrams or syntactic phase diagrams where liquid phase miscibility is present. So, let us look at it. So, that this is the typical phase diagram of syntactic reaction. Anyway, by the way, syntactic reaction is similar to like peritectic reaction. It is like L1 plus L2 giving rise to alpha here, giving rise to alpha phase. So, we know the peritectic reaction, this is a syntactic reaction, You know the peritectic reaction is what? Alpha plus liquid going to beta. Same like this is a similarity like this. This is a peritectic reaction. This is a similarity with the syntactic reactions. Monotectic reaction is similar to eutectic reactions in the eutectic phase diagram. On the other hand, syntactic reaction is similar to syntactic reaction. So, let us look at the phase diagram. See, the similar to monotectic phase diagram, it has a dome. You can see this is the dome. So, dome is a signature of liquid phase immiscibility. So, here also there is a Tc, okay. This is the Tc, this is the Tc, you see here, Tc above which single phase liquid is stable, and below this Tc, this liquid L separate into L plus N2. So, L separate into L1 plus L2 below Tc. This happens T less than equal to Tc. Now, at the syntactic reaction, this is a syntactic reaction, T syntactic. So, T equal to T syntactic equal to or less than syntactic will happen, T syntactic, that is where L1 plus L2 reacts and form, L1 plus L2 will react and form alpha phase at the syntactic reaction temperature. So, now if you go down, this is how things are happening. If you go down, nothing else will happen, okay, for the syntactic alloy, but depending on the hyposyntactic or hypersyntactic, the eutectic reactions can take place. There is two eutectic reactions on the both sides, one is U1, other is E2, this is the U1, this is the E2, okay. So, depending on composition, any eutectic reaction, either E1 or E2 take place, nothing else will happen. You can also have peritectic reaction on the both the ends. I will draw the phase diagrams which will have peritectic reactions now to show you, as that is not very difficult things to do. And well, before that, let me just clarify to you that there are very few systems which has this shows this kind of phase diagrams. This one is a potassium zinc system, which is not at all used in the real applications. And you see here, this is the dome, and then there is a line compound KZN3, it forms by the syntactic reaction KZN13. This again a line compound, and these forms this we have discussed in case of peritectic reactions. This is potassium lead system. There is compounds here, I guess, yeah, K2B Pb3, okay. K2Pb3 is forming by syntactic reactions, again here L1 plus L2 giving rise to this. So, well, now how the things happens in a syntactic reactions. So, before I do that, let me go back here and I take this alloy and I discuss. You can see here this alloy below Tc will separate into L1 plus L2. So, below Tc it will have two liquids L1 and L2, and both of the liquid will have different densities. Depending on density, either L1 will float or L2 will float. Let us suppose L1 floats on L2. Now, what will happen? As the syntactic reaction will happen, beta phase alpha phase will form at the interface. This is the alpha, and there is no further contact between these two liquids. So, reaction is going to stop at this below syntactic temperature, and these two liquids will undergo nothing else but these two eutectic reactions. So, you have eutectic reactions forming here between beta and alpha like this, and this one will have between alpha and gamma, okay, alpha and gamma. So, this is alpha and this is gamma and this is alpha, this is beta. That is what is going to happen, and this is exactly shown here. You can see here these two liquids forms L1 and L2. L2 is dispersed in L1. Well, there may be situations where rapidly solid cool it, then it will form a emulsion type of substance. Then L1 L2 reacts, form beta around it, and you can see once it forms beta, beta grows, and finally L2 and L1. As soon as beta forms, contact between L2 and L1 is over. So, L1 and L2 both remains, and finally from this you have beta particle, and you have a center you have L1, and outside you have center you have L2, outside of L1, and then this L2 will undergo eutectic reaction and followed by beta, and then you have another eutectic reaction in L2. Okay. That is what I am drawing. This is what is shown here. L1, L2 I just discussed, the beta forms, and then depending on what kind of things, it seems there is a periodic reaction on the right side and eutectic reaction on the left side. That is why L1 undergoes eutectic reaction and L2 undergoes periodic reactions. That is all it is. It is not very important phase diagrams, but I will just draw these two phase diagrams for your interest, and so and wind up this part of the course. Okay, let me just remove all this stuff and draw both the phase diagrams. We are not going to discuss about the free energy composition diagrams, because this is not a very industrially important alloy system phase diagram system. So, therefore, this is not interesting enough. We are simply, you should know it how actually things happens. So, you can see here that this is the phase diagram with a eutectic systems. So, you have eutectic, right, you have a eutectic mixture, and okay. So, this is L1 plus L2, L1 L2, this is your alpha, this is your beta, this is your gamma, alpha plus beta, alpha plus gamma, and this is L1 plus alpha, L2 plus alpha. This is where you have a syntactic reaction here. Okay, syntactic reaction is L1 plus L2 giving rise to alpha, and eutectic reaction on the both sides. This is E1, this is E2. Okay, now you can also have periodic reaction on both sides. So, let me just draw it. See whether, because sometime I also forget. Yeah. Okay. So, this is L1 plus L2, this is alpha, this is your alpha, this is your beta, beta plus L1 and alpha plus beta, this is L2, alpha plus L2, alpha plus L1, this is your this is your gamma, the gamma plus L2 and alpha plus gamma. So, you see the difference between these two are nothing, but here you have two eutectic reaction on both sides, there you have two periodic reaction on both sides. Okay. And you can also have peritectic eutectic mixture on the both sides, but phase diagram remains almost similar, that center part of it where the syntactic reaction happens. So, that is what I wanted you to concentrate, rest of the things are not required for these phase diagrams and therefore, we will not discuss further. So, this winds up our discussions on the phase diagrams of liquid systems. Liquid system means the systems in which your liquid phase is stable, and now we are going to discuss solid phase diagrams. Before that, I think I should also tell you the quasi chemical theory of how this kind of phase diagrams, different type of phase diagrams forms, and in the next class I am going to discuss the quasi chemical theory, and after that only we will move to the solid state phase diagrams.